sometimes the brief answers that are numeric or small expressions are also auto-recorded, auto-graded, because I can create a regular expression to track that.
Got it. Thank you.
All right. Any questions on anything not test related? I'll save those till after we go over the test. Okay, let's see, where are we? The 7th already. Already the 4th week of the semester. Getting close to being a quarter of the way done there. All right. All right. So begins test 2 area. That's the 2-dot nomenclature, numbering, whichever of those is correct, on our docs. First up is recursion. It's just a function that calls itself directly or indirectly. Our components. We need to have the recursive call, base case, and a production rule. All right, so if we have basic sum function, where we test a argument, and if it's under a certain value, we will not make a recursive call. Otherwise, we will make a recursive call on a different value. So our recursive call, right? Recursive call, the above is sum of x minus 1. Our base case is the test against x being positive. And the production rule is the x minus 1, something that changes x such that we're causing x to approach 0. So let's say we call int y equals sum of 4, for example. All right, so down here in main, we have our call of sum to 4. That brings us to our first sum frame. Sum 4 frame. So here we have x equals 4, and the return value is yet to be calculated because that's going to be sum of 3 plus 4. And so we will go ahead and just track x over here and the return value to be calculated later. Sum of 3, where x is going to be 3, and then that's going to have a return value. Sum of 2 plus 3. And we'll keep on going. Here x is 2, toss it off to the side, keep on going. Same thing over and over again with ever decreasing values. Sum of 1, x is 1. Keep on going. For our return value, I guess forgot to copy paste that part. Let's get all of our details. Down to 1 and sum of 0. 1 second. All right, and then we'll get over to one more. Sum of 0. X equal to 0. And our return value is 0. All right, so the previous call gives us back a 0 plus 1. And that yields back a 1. Previous, that gets sent along, 1 plus 2. That yields back a 3. Then we get ourselves a 3 plus 3. All right, that yields back 6, and then 6 plus 4. And then this turns out to be 10. All right, so this is a trivial example. A loop which would have the same big O, that being linear, would still outperform recursive version due to all of the stack frame overhead. But both versions or implementations still growing at the same rate. That's the same. There you go. All right, so you may or may not already be familiar with recursion. Hopefully you are, and this is just a review, but typically we have a non-linear problem. A recursive solution will be a better fit to solve that problem, as our linear options would be more complex code to solve the problem at hand. All right, so if we go and look at files section, where is my recursive code? There we are. So there's several examples in here that are fairly trivial. You can take a look at them yourself, and we'll look at how bad a couple of them are. But here we have permutate, which I did not write. I think I took away the comment where I got it from because the website disappeared. Anyways, grab that part and then the call to it in main. All right, so it's a simple output here. Pass in the numbers 1, 2, 3, 4, and 5. And then we just go ahead and show all the different ways. The 1, 2, 3, 4, 5 can be arranged, right? So we swapped 4 and 5, those get put back. Then we do we swap 4 and 3, right? Those got put back, and then we just do more swapping. So we see 1, 2 sticks around a little bit, then 2 starts swapping, and the number of solutions grows significantly. Or if we do the same problem only for 3 elements, right? Just 6 permutations. If we go up one more, all right, it goes up quite a bit, goes up to 24, and then back to our full size here, going to 5, where we have 120 different permutations. Right, not to be confused with combinations, which you get into the math class, but these are all the same combination because it's all the same 5 digits, but the order matters in permutations. All right, so this particular code example is going to be well beyond anything you would see on the test, but it is simply a good example of a useful recursive method. Right, here's our method name, permutate. Here's our method call in here. Right, base case being tracked by this loop here, where the loop controls how often we call the permutate here, and then these values are changing. Right, k changes as we make our recursive call. So there is our production rule. Keep changing k. So that every time we get deeper and deeper and deeper in, we're dealing with a smaller subsection of our array of data. Right, recursion is not always solution. Here is Fibonacci. Right, Fibonacci is just 1, 2, 4, 5. All right, so we'll go ahead and loop through this a few times. And spit out some Fibonacci. Let's do my extra output. Above. Yeah, we should go a little bit further. Let's go to 7. All right, some of the previous terms. So a couple of definitions, Fibonacci, whatever first 2 terms here we're saying are 1 and 1. There's also a definition saying it's 0 and 1. So that aside, 1 and 1 gives us 2, 1 and 2 gives us 3, 2 and 3 gives us 5, etc., etc. Just some of the previous 2 terms. But what we're doing here is what's known as tail recursion. All right, so tail recursion, the only recursive call is our on the last statement of code. This can be re-implemented with just a loop. Back when I was reading my recursion law, the book had this example doing Fibonacci recursion. I started reading them. I'm like, what the heck? And I had to go write the loop if I could do it, and I could. And then, like next paragraph, so you could rewrite this as loop. I'm like, I should have kept reading before I got a little overexcited and jumped on the computer. But hey, writing code is the best way to learn how, of course. All right, so this Fibonacci, if we try to calculate, where's my annotate? If we want to calculate, right, the Fibonacci of 6, and that is equal to the Fibonacci of 5 plus the Fibonacci of 4. Hopefully you can read that. 5 is going to become Fibonacci of 4 and 3. Just like the Fibonacci of 4 is going to become that of 3 and 2. And here we've calculated Fibonacci of 4, and over here we're going to do it again. 3 and 2. So we're redoing work. That's always bad practice for a computer program to redo something. 2 plus 2 is always 2. 2 times 2 is out. 2 plus 2 is always 4, and 2 times 2 is always 4. Calculating it again is not going to change the result. Right, so always good Make sure you use recursion in a very, very limited context. It's a very niche area. It has its practical places. And when we start getting into our nonlinear data structures, we're going to see this used a little bit more often. But once you use it, learn this tool doesn't just mean start applying it everywhere, because it's not always applicable to everything that we're going to be doing. There are a few more code examples in here. Some of them can be improved even more so. All right, so our first version, make that a little bigger. For a summation like we saw on the whiteboard, right? Basic recursion. I had a slightly different version where I said less than 1. Suppose the less than equals 0. Return 0, mathematically the same. Right, this is a loop in disguise, right? Summation, calling summation, calling summation. We're going down by 1 each time. Basically the same thing as a loop. Right, so we have here our loop counterpart. Same story, same complexity, linear. We have a looping component. Here the looping component's easy to see. It's a for loop. Here the looping component is less easy to see. It's the recursion, because it's being done via recursion. And here we have the same answer to the same problem, using a mathematical expression, turning the problem down to a constant time. All right, so if we're going to choose amongst the first two options, the recursive versus the iterative, we want to take the iterative because it has less overhead, even though it has the same O notation. But then we come in with an additional option for doing the summation series with the mathematical representation. Right? You can get into the math in the computer math class, but constant is going to be the winner versus linear. And that's all there is to this code file. And I will make a note to make sure I post some links for recursion. As soon as I find my notepad. There it is. Any questions at the moment for recursion? And we'll be swinging back to it as we move along and keep making it work for us. Right. Stack frame overhead means every time you call a function, that means you need to allocate a frame on the stack to track local variables, parameters, return addresses, return value. So it's just a memory allocation. And it's not a particularly expensive thing, but if you get a little bit crazy, you get to a Stack Overflow, which is where that website gets its name. It's Stack Overflow is recursion gone awry, where the recursive functions just keep calling themselves because the base case wasn't well formed, and we managed to never approach it. Like there was a point in time where we were getting closer, and then we just never quite got there. It's like trying to get to 0 by dividing 1 in half, right? And then you can divide it in half again, and then you keep dividing it in half. Mathematically, you'll never get to 0. In a computer, you would, because eventually you'll run out of bits in the storage space for it. But mathematically, you would never get there. So if you have an unsized, unbounded numeric representation in the computer, your recursive method would never get there. But because computers can divide it by 2, right, that would get there. So let's demonstrate. And whatever having. And not an int. Let's make that to double. Let's keep it reasonable. Let's make it a float to start. If number is equal to 0, we're done. Otherwise, we're going to go ahead and spit the number out. Just a little bit of white space. And then call ourselves again with half that number. So if we go ahead and call having 1, 2. Let's see how long it goes before. Da, 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 da. Turn 0. Never really actually using anything with that numbers, but there we go. And we could do a little more white space. Let's change that to an inline. That didn't go too far. And this is how base 2 numbers work. All right, cutting in half, we're just basically shifting that bit over by 1. Halves, 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 halves. Numbers getting closer and closer and closer and closer to 0. Actually gets to computer 0, but mathematically we should keep on going. When we get there, about 20, 30 calls. How many calls do we get here? Yeah. Let's see. Count. I'm curious. 150. And so we got 150 times before we quote unquote got to 0. It's a lot of stack frames. All right, we could have done the same thing with just a loop. All right, x equals 2 while x. All right, and same thing. X divided equals 2. Spit it out, all that fun stuff. And the runtime should be a little bit faster. It helps if I use the same data type. Things will work a lot better that way. All right, of course, same progression of numbers, but of course, the slowest thing in this is going to be actually spitting out to the console. But again, tail recursion. Tail recursion is not basically a good recursive model. And here we do actually have a bad, slightly bad. Let's see, what does negative numbers do? Is it going to freak out? It didn't freak out. And the negative number is still up to 0. Anyways, so our base case is okay, even handles negatives. Sometimes negative numbers can throw us for a big curveball. All right, next up is the major area of focus for test 2, that being sorting. Sorting data, which we'll presume to be an ascending sort. Something that takes a fair amount of work. And there are numerous ways to solve the problem. We'll only be looking at a small subset of those. All right, so our basic example, bubble sort. All right, so our algorithm, repeatedly compare adjacent elements. If those 2 elements are out of position with respect to each other, then we'll swap them. If not, we'll carry on. All right, so state being the left, 0 will be our initial data state, 3, 4 as we make changes. This table's gonna have to get bigger. Index is 5 values. And we'll go ahead and sort 9, 5, 1, 3, and 2. So what we're going to do is compare the very first two elements. If they're out of position, we will go ahead and swap them. And nobody else moves. Next, compare 9 and 1. If they're out of place, we'll swap them. They are, so they get swapped, and nobody else moves. Since I have the largest value all the way at the beginning of our list, it's going to keep on swapping everyone that it sees. Try that again. 9 and 2, 5, 1, 3, 2, and 9. And 9 is now in its final sorted position. All right, that is sorted.
I have a question.
Mm-hmm.
What do you mean by like if they're out of position? Like what does that mean?
Right. In ascending order, 9 does not belong to the left of 5.
Oh, okay, got it.
Yep.
Wait,
Right.
but then why is 1 after 5?
Because we haven't compared them yet. Right?
Oh, okay.
We only compared, right, so bold is the compared values.
Okay, thank you.
Mm-hmm. All right, so that's the codes can just be a pair of nested loops. That was one inner iteration through the loop. So reset back to the beginning. I'm going to go ahead and copy this whole row here. Call that state 4A. And we're repeating. We'll compare the first, try to compare the first two elements. We're going to state 5, 5, and 1 were out of position. So we swap them, and 9 remains where it is. Then we're going to go ahead and compare 5 and 3. 5 and 3 are out of position, so they get swapped. Rinse and repeat. 5 and 2 are compared. They get swapped. And that gets us to 5 in its final sorted position. So just draw the state. 1 and 3 are compared. They're already in respective order, so no swap is needed. 2, 3, and 2 are compared and swapped. And that gives us 3 in its final sorted position. All right. 9A, we start over. We'll go ahead and compare. And 1 and 2 don't need swapping, which makes 2 in its final sorted position. And then we're down to a single element. And there's no other possible way that one element can be arranged, so we are finally sorted. All right, the code is a nested pair of loops. Inner loop, first time through, goes through almost every element. Each subsequent pass is one shorter than the previous. The worst case here was the first loop. So we have linear component. That component is wrapped inside a loop looking through most of the entire list, which is also linear. Overall, big O is n squared. Let's see if I can find where change. Never find it. Text superscript control plus dot. All right. Big O n squared. The algorithm sort of makes sense. We just keep comparing adjacent values, swap if needed. Code. Sorting. Sorts code file should have all of our basic sorts. All right, bubble sort. Takes the array, takes how big the array is. We're gonna have two nested loops. Test to see if they're out of order, right? Testing J versus J plus 1, adjacent elements. If they're out of order, go ahead and swap. If they're not, we did nothing in that loop, and we just go ahead and increment J. And so we're out of loop I length -1. This is tracking how far down the array to bubble a value. So the very first pass, we're going to bubble all the way to the end of the array, right? Because the length is 10, that means 9 will be the last valid index. We go I greater than 0, so we don't actually hit the 0 element, which is why we're almost every element. Our inner loop, J starts on the far left side, compares less than I but not equal to, so that we stay within bounds of the array because we're going to be adding +1 for J. All right, so I 9, J to 0, J less than 9, assuming a 10 element array. Compare 0 to 1, needed swap. Compare 1 to 2, needed swap. 2 to 3, 3 to 4, et cetera, et cetera, et cetera. 8 to 9, if needed, swap. And then we're done with our first loop. I decrements down by 1. Now we're going to the 8th position in our 10 element array, or the 8th index, 9th position, and do the same thing over and over again. We do have an optimization in here because it's entirely possible that we're being asked to sort an already sorted array. So this test flag is going to let us know if we did any swaps. So the very beginning of the outer loop, we initialize the test to 0. If there's a swap, we'll turn the tag on. If there's not, so we go, the numbers in our array are 1, 2, 3, 4, 5, going through 10. 1's less than 2, so we don't do anything. 2's less than 3, don't do anything. 3 less than 4, so on. 9's less than 10. We never set our test flag. We can see that we can bail out of our loop because the list is already sorted. It's possible it's already sorted to start off with. And it's possible we got lucky and it was semi-sorted and we only had to move a few values. So that's just a little extra memory to give us a little bit better average runtime, but our own notation is going to be the same. Worst case scenario, we're given a descending list, 9, 8, 7, 6 down to 0, 9 bubbles all the way to the end. Every time it's true, bubble. Then 8 bubbles all the way down to the end just before 9. Then 7 does the same thing. Then 6 does the same thing. That is our worst case scenario. And worst case scenario, of course, is what we do for big O. Giving us our squared O notation. Any questions about the code on the screen? All right. Our next sort Selection sort. Sorting. I can type and or spell. Selection sort. All right, so our algorithm here is to logically divide the array into two partitions. One sorted and the other unsorted. We'll repeatedly take the largest value, smallest value from the unsorted partition and append that to the sorted partition. All right, so repeatedly, initial state, the sorted partition is empty. Remaining elements are the unsorted partition. Starting at the first value of the unsorted partition, we'll set that to be the smallest value and iterate through looking for someone smaller. All right. So like before, we'll have state and index. And might as well use the same values. Grab those. All right, so initially, we're going to flag 9 as the smallest value. Then we'll go ahead and see that 5 is smaller. And we're going to keep iterating down, comparing values against the smallest value we've found thus far, and iterating down, looking for someone smaller, looking for someone smaller, until we've identified 1 as the smallest value. And then we'll go ahead and swap to the end of the sorted partition. Let's bold our candidates, the smallest value, and orange final sorted position. All right, so 9 did get swapped, so I'll underline with 1. That's our first real state change where we move things in the array. And we'll carry on from there, repeating as we did before. We'll take this first value, flag that as the smallest, and repeat. Looking for someone smaller. 9's not smaller, so keep on going. Find that 3 is smaller than 5. I'll mark that as our smallest. And then we find 2, 1 out over 3. And then we can go ahead and do a swap. 2 and 5 swap positions. 2's in its final sorted location. 5 had swapped with it. All right, and then now we're going to go ahead and abbreviate things a little bit. Look until we find the smallest value. That is 3. That's going to cause a state change. 3 gets swapped with 9. Try that again. 3 is in its final. Sort of wrong. All right, italic. Underlined value was swapped. Rinse, repeat. Right, 5 is identified as the smallest number. That gets swapped into sort position, right? Appending it to the end of our array, leaving us with 9 having been swapped. And then the last element is the last element, and there's nothing to do at that point. And our array is sorted. And the code, also a pair of nested loops. Inner loop is looking for the extreme value. It's smallest in the case of ascending sort. Ascending, largest for descending. And after we're done looping, you can swap. Outer loop repeats for every element. Every element, each loop being linear. And so our overall big O here is also big O n squared. N squared, let's see. Nope. Don't know why I can't get the format to work, but it doesn't work. Questions on the algorithm at this point? All right, the code. All right, selection sort. This one, the example code's all just embedded right into the loop instead of passing it around. So not a very good function design because it only ever works on this one array. Much better function design, of course, is to pass the data that a function needs to do its job. Thus you can call it in more than one way. All right, for loop. Find the smallest value. All right, so we're tracking it by index. So we initially set index equal I. So the very first element, 52, is our smallest number. Until we find someone smaller. I found 1 is smaller, not smaller, not smaller, not smaller, not smaller. We get to 0. That was smaller, so we update our min index. Here we do have a little bit of a micro optimization. Check to see that there's actually work to be done. Min index and I are the same. There's nothing to swap. And if they aren't, we'll go ahead and swap the two values. And then we've completed the body of the outer loop. I goes up 1. Do it all again. Now 1's the smallest value. Keep on going until we find someone smaller. We didn't because 0's already been moved up to the front. So we didn't actually have to do anything. This test was always false. That was never set. So the swap didn't have to be done. Rinse and repeat. Notice we don't have a test flag with this code. There is no early out. This one with the bubble sort, we actually have a best case O notation of linear. If you give it an already sorted array, it'll test the array by making one pass across the whole array. See that everyone's already in their appropriate position and then bail out. Here, there's no such opportunity to optimize the selection sort. It doesn't know it has the smallest value until it's actually inspected every value in the unsorted part of the array, which means looking at every single value in the array. Even if these were all sorted, it wouldn't know that it had the smallest number until it got to the end, but at least it doesn't do any swapping in the best case. So there's 0 swaps in the best case. But the best case O notation is still n squared. Okay. Questions about selection sort before we carry on to our next? Everyone's brain is drained from the test, so we're saving up all the questions for another time, right? Insertion sort. All right, so our algorithm here is to also logically divide the array into 2 partitions, a sorted and unsorted partition. We'll take first value from the unsorted part and insert that into the sorted part. That's where it gets its name from, because we're just going to be doing in inserts. Initially, sorted partition is the first element. Remaining elements are the unsorted part. We'll shift values over to make room for the new data point as needed, such that we can drop that value into sorted location of the sorted partition. All right, let's get our table going. Okay. And may as well use the same values. They're unordered. All right, so right now we'll put a divide line here. Nine is our sorted array. 5, 1, 3, and 2 are our unsorted part. So what we want to do is put 5 into this sorted array. So what happens, mechanically, we'll copy 5 off into a temp here somewhere so that we are free to go ahead and overwrite 9 on top of it, freeing up this position and dropping 5 in. All right, so we tested 5 against 9, found that 5 belongs to the left of 9, so 9 moved over to the right to free up a space to its left. Then we would have tested another value if there was another value, but there wasn't. We hit the front of the array, so we go ahead and stop and drop the value in there, and our sorted part is growing. Next up, we'll grab 1, set it aside, compare 1 to 9, see that 1 belongs to the left of 9, so 9 will go ahead and overwrite. 1's considering this position between 5 and 9, sees that it does not belong to the right of 5, so 5 will go ahead and shift over to the right, and then 1 drops into the beginning of the array. All right, we'll repeat the process. Set 3 aside, compare 3 to 9, 9 makes way. Compare 3 to 5, 5 makes way. Compare 3 to 1, 1 says you don't belong to my left. So we go ahead and drop in the value. Dropped in 5, dropped in 1, we dropped in 3. And our sorted part has grown. All right, again, we'll do the same thing. Set 2 aside, 9 shifts over, 5 shifts over, 3 shifts over. We have a void here, and 2 drops right in. So let's see, let's underline our shifted values. That had to shift, those had to shift, and had to shift. But our array is now sorted. All right, so our code. Again, a pair of loops. This time, the inner loop is going to be a bit more random as to how many times it needs to iterate. In the worst case, we'll have to shift every value in the sorted part to make room for the next value who is lower than all of the sorted values. So we'll be linear in that case, and we need to do that operation for almost every element. Every element of the array, which is also linear. All right, so as we had before, our big O, there's the big O n squared. Our best case is a little bit more better off here. Our best case scenario would be an already sorted array, which case grabbing the first value and comparing it to just one value is a constant cost, and making the algorithm go in just like bubble sort could be. All right, we already have the data 1, 2, 3, 4, 5. All right, 1's our sorted list. Look at 2. 2 is greater than 1, so stays where it is. Next, we grab 3, compare 3 to 2. 3 is greater than 2, stays where it is. Same thing for 4, and same thing for 5. No shifting, which is our linear component in the inner loop, needed to be done. So all we have is the outer loop to grab each of the values from the unsorted partition. All right. Let's see, where is, there's my insertion sort. All right. Right, for loop, for loop. That's it, for loops. Here's where we go ahead and set aside the value. By setting aside this value means we don't have to swap with insertion sort. And instead we shift the values. We just go ahead and stomp on the value to the right, the value just to the left of it. And we can do that because we set aside the first value. And we'll just keep on doing this while we are within the bounds of the array and the key and the value that we're looking at are out of order. All right, so we start at the end of the sorted part of the array, work our way down towards 0, shifting values as needed, and then we drop the value into its sorted position. So in the best case scenario, we're grabbing the key and then we're dropping the key right where it already was because I didn't change. This case was false to begin with. We never enter the loop and we drop it right where it was because I started at j minus 1 and then minus 1 plus 1 offsets, and they're at the same place. Questions about the code or the algorithm or any of these three sorts? The best case and the average case for all three sorts are n squared. So the worst case, average case are all the same. Best case, insertion sort and bubble sort are linear. Just one of those random chance scenarios. You can, if you wanted to, for the selection sort, added an extra am I sorted check to try to, if you think for some reason your library does use selection sort as its algorithm, and you know a reasonable part of the time that the data is already going to be sorted, then doing that extra effort up front, which is just a single iteration across the loop to save n squared, right? That is going to be a useful thing, but if it's not a likely situation, then it's just extra overhead. All right, let's go ahead and take a 5-minute break, try to digest our sorting a little bit. And then we can come to our Quicksort algorithm, which is what C standard library uses, and probably several libraries, but it's certainly a lot more to chew on. So going on mute, back in 5. All right, next up on the plate, Quicksort. The algorithm here is a fair bit more complex. What we're going to be doing is dividing, if I can type, spell, the array into two parts. One part will have all the values in the array that are less than a pivot value. Less than a pivot, and the other part greater than the pivot. If there are duplicate values, that would go to one of the sides. Pivot value is selected from among the values in the array or part of the array that we're sorting. We'll get into how we select those in a minute. After all the values have been categorized, we'll swap the pivot in between those two sets and have placed that pivot value all right, pivot value to its final sorted position. Then we'll recursively call the algorithm for both sides. The values less than the pivot, and the side with the values greater than the pivot. All right, so we're talking about three different ways we can select the pivot. First one, simplest one, we take the first value from the array, or part of the array. Second one, we can take the median value from the array, all right, so whatever is in the middle of the array. Or we can take the median of 3. Median value. This one's by index. Median of the first, last, and middle. In fact, let me change this from say median to say middle value. Get my terms cross-threaded. And middle positions of the array. All right, so for example, using option 1, taking the first value as the pivot. And I can make this one a little bit bigger. State and index. And carrying on. Okay, let's see. We'll put 5, 9, 2, 3, 7, 4, and 1 as the values we're going to sort. So we're going to select 5 to be the pivot. Well, that's hard to see, so let's go further that way. All right. What we want to do is look for values that are going to belong in the left partition and values are going to belong in the right partition. These partitions aren't set in size yet. How big the partitions are going to be completely driven on the data. We're going to go ahead and do start on the left-hand side and look at the first value. You can see that the first value is larger than the pivot. Since it's larger than the pivot, it does not belong in the left set. And we're going to start by building the left set. So we'll go ahead and jump to the opposite side and look at 1. 1 is lower than the pivot, and that does not belong in the right set. So what we're going to do is swap those two values. One and 9 gets swapped. And then we'll repeat. We're going to keep growing the left set. Next value here is 2. 2 is less than 5, so it's happy where it is. 3, less than 5, also happy where it is. 7, it's not happy where it is. So we'll go ahead and flag that for swapping. Jump to the right side. We find 4. 4 is not greater than the pivot. So we're going to go ahead and do a swap. Those two values. It's a bold swapped state change. Underlined values found in the wrong partition. All right, so we've now defined our two sets. So we have 1, 2, 3, and 4. These are all the values that are lower than 5. And then we have 7 and 9, all the values that are greater than 5. So green set is lower than the pivot. And our blue set is greater than pivot. So now what we want to do is go ahead and put 5 in between. So 4 we'll swap with the pivot. And we have, let's see, there's a way to clear all formatting. Error. 5 in its final sorted position. Why did my font get small all of a sudden? Interesting. Oh, because I cleared all the formatting. I gotcha. All right, so as before, orange. Final sorted position. All right, so let's look at the logic here. There is no possible other place that 5 can exist with the other values that we have. Everyone to its left is smaller, and everyone to its right is bigger. There's no other index that 5 can occupy with the data that we have here. So that will carry through. We'll get back to that later. Now we get to our recursive call, where we're going to go ahead and sort, quick sort the left position, repeat the process. The first value is set as the pivot. And then we're going to go ahead and look for people that are out of position. All right, so we're going to start building the left set. 1's less than 4, so that's happy. 2 is less than 4, also happy. 3 is less than 4, also happy. and then we're out of the bounds of the range, so we're done. We've created a left set. The right set is empty, so it's a non-ideal split, but that's going to happen. We will swap our pivot to the end of the left partition, putting it into its final sorted position. And we're going to rinse and repeat. 3 becomes the pivot. We will get the same bad split. But we're at least working our way there. Eventually we will get this in sorted order. And sometimes our split will be better than what we have here. It's one of the reasons why we have median of 3 as our pivot selection criteria, because sometimes we are selecting the extreme value. The extreme value is not a good pivot value. One and 2 swap over. 2 gets to be in its final sort position. This guy is no longer the pivot. And then a 1 element array is by definition sorted, so we don't need to do anything further at that point. So digging back up, unwinding our recursive stack, we have those elements in their final sort position. And we have 7 and 9 with which to process. 7 is set as the pivot. We get to a 1, we find that 9 is in its proper right side, where we see that this is in the left side. Right, so the left side finds 9, says you're out of order, then we jump to the right side, finds 9, and comes over here to 7 and finds that we're going to put 7 right exactly where it is. So 9 is actually going to be the right set. So 7 swaps with itself, putting into final sorted position. And then we get our 1 element array 9. 1 element arrays are sorted by definition. And we're finally done. All right, so our code here. Still nested loops. And those loops might be going as far as the entirety of the array, each of which are linear components. And so the big O is going to be log n, not log n squared again as usual. But n log n is going to be our average time. All right, so let's go take a look at the code. Back to files, grab Quicksort. Okay, Quicksort. All right, this is a recursive function as mentioned earlier. So here line 76 and 82, we have our recursive calls, parameters in the array, and then the section of the array that we're working on. So the very first call would be I think 8 should be 5 on line 20. Check what I did over here. Line 20. Oops, thank you. Typos. Good spot. All right, so the first call if is a 10 element array, 0 and 9 will be our initial boundaries that we're going to work with. This particular approach is doing the second style, where we're going to use the middle value. So we'll set the left to the beginning plus 1. So this is the left edge that we're going to start building from. Set the right to the end, the right edge that we'll be growing from. We're going to swap. Beginning is 9, 9 divided by 2 is 4. Right, integer math, just like with the binary search, and swap those two values. So we're going to put the pivot all the way at the beginning of the array. And we're going to set aside the pivot into its own variable, right? Micro optimization, so we don't have to keep array indexing over and over and over again. Our base case for our recursion is to make sure, or let me get ahead myself. Base cases are over here, making sure that there's actual work to be done before we call Quicksort. Make sure the beginning and right have not crossed over, sort of thing, and the right and then haven't crossed over, sort of thing. Our loop condition, we're going to keep building our left and right partitions until they cross over. So inside the outer loop, our first loop working on the left side, boundary checking, left versus the end, and then the actual work of comparing the values. Is the value that we're looking at a candidate to belong in the left set, belong in the left set. If that value is less than the pivot, it belongs, and we can go look for the next person. So left goes up by 1. All right, some debug code, spit it out, and you compare to see if that candidate belongs left set. If it does, left keep going left, we'll just keep incrementing. If it doesn't, we found someone who's out of position, so we stop incrementing left. Right, so the job of this loop is just increment left until we find someone who's out of place, which could be immediately, it could be several down. Then do the same thing on the right side. Make sure we don't go out of bounds of the array, and then the work of checking versus the pivot. That value is greater than the pivot, then we're where we belong, and the right can decrement. If it's not, the right stays where it is. We found 2 positions out of place. And if we found them, go ahead and swap. Otherwise, a correction to force us to get out of the loop a little bit earlier because we found the crossover position. Here is the sorting step, actually getting the value into its sorted position. And then good old recursion. Do it all again. Do it for the left half and do it for the right half. So quite a bit more code here than we have with our other sorts. Much more significant involvement. And see if we run this code, it will run in random fashions, randomly building the data. Lost server connection. Oh boy, that's just terrible. Session timed out, I guess. Good thing we had the code somewhere else. Always good to have backups for your code. Everyone still hear me? Okay, good. You're commenting. Good. Make sure it wasn't my internet connection.
Yeah, we can hear you.
All right. Something's working. All right. Well, we've got offline options here. Pointer.
Professor,
Go ahead.
how do we go about picking the best type of sort? for problem.
For step 1, compare the annotations. Step 2, understand the circumstances in which you're sorting the data. In fact, we're going to look at a YouTube video here in a second. If this will run for me, try it again. Be really helpful for a little. There we are. Right, so this is what the code will look like, a bunch of random numbers. We chose the middle element to be the pivot. It's an okay pivot. There are 2 values that are less than it. Move the pivot into sort of position. So we're going to start left and right at 1 and 9. Right, the very first value we found, 809, out of position. So we go ahead and jump to the right side, get that down there. 809 and 310, swap over. So 310 is down the left side, 809 is on the right side. So the right side are these 3 elements. Left side is this 1 element. 703 out of position, going again, decrementing down till we find 164. These 2 values will swap. And we have our left partition. We have our right partition. And then we can go ahead and swap 322 into its final sort of position. Right, everyone lower to the left, everyone greater to the right, and recurse, look, dig, find, and carry on. So what is the best sort? It's always an important question. Okay, that's not what I want. I want this one. That's still not the one I want. Side by side source. That's what I want. All right, good old YouTube, which I need to mute here because not exactly useful sound. And then we pause, slow this down, and start it over. So this is a random set of data. All right, patience. Okay, so let's see. Make this try to fit your screen. Let's go. That's not bad. All right, so we have here top left selection sort, shell sort. We're not going to talk about insertion sort. We talked about merge sorts coming up next. Quicksort, when we just talked about heap sorts for down later. Bubble sort we also talked about, and then these last 2 we did not talk about. So it's going to be core speeds probably. That's good. Right, so you can see insertion sorts grabbing a red value and then inserting it in proper position. Selection sort, here it found the smallest value, swapped it, looking for smaller values. So the red one's tracking the smallest values, swaps it. So the red possibly moves as it finds others that are smaller and then swaps it to the beginning. Bubble sort, right? Large value, the red bar just keeps growing until it gets to the top. And then the next largest red value keeps growing until it gets to the top. And Quicksort's already done. So let's go and pause it right there. So we see selection sort has not made a lot of progress. Shell sort also done. That's also a good algorithm for a random set of data. Insertion still working. Heap is also a similar complexity class, but there's a little bit more overhead. We'll talk about that one later. And he's also bubble sort still because of the overhead of the swapping. Swapping is a fairly expensive operation, right? It's got 3 copies, copy. And things move along. So speed this up a little bit. There you go. See, merge sort caught up. So it looked like it wasn't doing a lot in the beginning because merge sort, there's a lot of run up work to it where it's dividing the arrays in half and half and half and half. And it does a little bit of a divide and conquer solution where we make the problem smaller, just like the binary search was, make the problem smaller, and then work with small problems, making them up to the bigger end solution. Right, you can see heap sort's nice and consistent, getting its way up there. Comb sort, almost done. Insertion still trying to get there. Almost there. Bubble sort. It's got a long way to go. Right. Bubble sort is definitely an academic sort algorithm because it is the simplest to code. Selection sort being the next simplest to code. And insertion sort is not too bad for an academic one, but you can see there's clearly better ones in terms of actual time. Right, so we're not doing O notations. So the O notations for a lot of these are the same. N squared is the common O notation amongst these 9 sorts. Yeah, so then that's why they call it Quicksort because it is quick. On average, it is N log N. Right, these are on your big O cheat sheet link that we looked at last week or the week before. And we'll just go ahead and skip along because we gotta skip along because bubble sort's still trudging along here. This one's for few unique values, right? Because the nature of the data can drive what algorithms are going to work the best. And you see Quicksort still the winner in this particular example. All right, the merge sort. See how it's doing divide and conquer. It got lists brought them together. This one's making small lists, bringing them together. Then it's going to bring them together, and then do the same over here. Get another step ladder like we have that's like this one, and then they all get merged up. You see shell sort's already completed. Merge sort's getting pretty close. Insertion is still working, but it's made a lot of progress. Heap sort's getting there, and bam, merge sort's done. And heap sort caught up, comb sort, and heap sort a little bit of a tie there, but as you see, our insertion sort's the only reasonable one of our academic ones, and cocktail sort's doing quite poorly with this data set. Skip along, right? Reverse order. So now we're getting the worst case scenario, which is where our big O notation truly applies. It's not going to be the worst case scenario for everyone, especially depending on how Quicksort selects its pivots. If it's a good pivot selection method, then we're still doing middle values, even though we have to do a lot of swapping. Here, bubble sort's got to swap everyone all the way across. We can see those red bars always red as we go all the way across. Insertion sort, same thing. Red bars going all the way across. Selection sort, it's the same. It's just the minimum value moves along, and then there's a swap. And since we're swapping the first to the last, it's actually putting large values towards the end, but it's not going to really much matter. Just gonna be less swapping in the end there. But yeah. And there's a few more here. You have the link. It's in Canvas sorting section. All right, there's a visualizer. All right, hackerearth.com, and we'll go ahead and 1, 5, 9, 3, 4, 7, whatever. Let's see, that's 6 values. I need a couple more. All right, select the sort, and then you can see what it's supposed to be doing type thing in the stepwise fashion, or you can fast forward it. Now, bubble and selection are useful for O notation principles and just getting the basic ideas of sorting. Otherwise, yeah, you won't see a library implement. You shouldn't see a library implementer using those as the implementations. Okay, let's see. We've had 10 minutes of breaks. We still need 30, so it's 20. Okay. We're going to go ahead and stop there for lecture and roll into the test. So let's go ahead and stop the recording, please.